We'll wait for a few minutes and then we'll start. I'll start in a few minutes. Right, so I'll share my slides. Meanwhile, if anyone wants to join, please admit them. Right. Welcome to the 8th live session of structural biology. So in this class, we'll be talking about microscopy, whether that is light microscopy or electron microscopy or cryo-electron microscopy. So to begin with, there are many limitations of the normal eye. So the normal eye cannot see objects less than 100 micrometer in diameter. So if you look at this, which shows the limit of the naked eye is up to 100 micrometer. So at the maximum, the naked eye can see the micella formed by different fungus. But beyond that, the cells, the viruses, the bacteria is beyond the scope of the naked eye. So initially, hand lenses were used to provide enlargement of objects from 2 to 10 times. They were the first and the simplest microscope. Then the light microscope was introduced, which uses visible light and a system of lenses to magnify the images of small samples. So if there is a small object here, and you imagine two rays of light, one passing through the middle of the lens, which is undeviated, and one which passes through the upper part and is refracted. Both of them converge at the focal point, which falls on our eye. And when the eye looks for the image, the eye cannot bend the ray. So the eye will imagine that the ray, that if you imagine a straight line drawn from the ray, the eye forms a virtual image of the object, which is much larger than the actual object. And this is the principle of the light microscope. So this is a simple microscope that is using a lens to enlarge an object through angular magnification alone, giving the viewer an erect, enlarged virtual image. So the image that the eye is seeing is virtual, meaning it does not actually exist. It is just an imaginary image of the object, which is enlarged by many times. This lens has been used over the years in simple devices such as magnifying glasses. Now, if you look at the limits of the light microscope, the light microscope limit also ends at around 0.25 micrometer. So using a light microscope, you can see the different eukaryotic cells, yeasts or bacteria, and even some mycoplasm, but you cannot see viruses, which are less than 0.1 micrometer. For that, you will need the electron microscope. So after the simple microscope, the compound microscope was invented. And what it does is that in the simple microscope, you had seen that there was one single lens. In the compound microscope, there are two lenses. One is the objective lens, which is close to the object being viewed. And what the objective lens does is that it collects light and focuses a real image of the object inside the microscope. So this is the object. The rays of light from the object pass through the objective lens and are focused to give a slightly enlarged image 1 near the eye. This image 1 is magnified even more by the second lens called the eyepiece lens. And this, so then from the image 1, the rays of light reach the eye. And when the eye reconstructs the image by drawing imaginary lines back to where they meet, it gets a hugely magnified image of the object. So the magnification in the compound microscope is much greater than that of the simple microscope. And it depends on 2 times magnification. First, by the objective lens, which creates a slightly enlarged real image, and then by the eyepiece lens, which creates a hugely enlarged virtual image. And this is the image that the eye is seeing. Now, in microscope, there are many different kinds of aberrations. One is the spherical aberration. So this happens when the light rays hitting the periphery of the lens are more refracted than the light rays hitting the center. So this is a light ray hitting the center. It is almost undeviated. But as you move to the periphery of the lens, the light ray gets more and more bent. And that is why all the light rays are not meeting at a single focus point. If this is the case, then you will get a very blurry image. Because if you look at this example, this is the case when the light rays are meeting at a single point. Only if it is meeting at a single point will you get a cleared object, clear image. Otherwise, if they crisscross each other like this, a blurry image of the object will be formed. Another aberration that is often present in microscopes is called the chromatic aberration. So here what happens is white light, when passing through the simple lens, each of the wavelengths are refracted to different extent. While the blue wavelength uh, uh, meets at a focus point which is short, the red wavelength meets at a focal point which is long. So like this, the white light which enters the lens is split up into its component wavelengths, and again you will get a blurry, color distorted image. So this is another common aberration that is present in the lens of the microscope. Beyond the compound microscope, there were several advancements of microscopy. One of these is the confocal microscope. This has attracted wide attention as an alternative to X-ray crystallography or NMR spectroscopy for macromolecular structure determination without the need for crystallization. So what happens in the confocal microscope is that there is a point light source and the light passes through a small hole. Here it meets a beam splitter. So what the beam splitter does is it deviates some of the beam to pass through the objective lens onto the sample, and it deviates the rest of the beam to reach the detector. So you get a background uh, uh, image that is in absence of the sample, and you get the image of the sample which is reflected from the sample uh, separately. So you can subtract the background and get the image of the sample in good focus. Now, if both these beams after splitting are meeting at a single point, then you will get a good focused image. Otherwise, if the two beams are spread out like this, then the image is very blurry and spread out. So that is the confocal microscope. But the most recent and advanced type of microscope is the cryogenic electron microscope, or cryo-EM. So the electron microscopy technique applied on samples cooled to cryogenic temperatures and embedded in an environment of vitreous water. So we learn more about the details of this technique later, but just to learn it in a very short way is that the sample of the protein is first purified, and then it is cooled to then it is mounted on a grid. After the mounting, it is cooled to very low temperatures such that all the water that is in the sample is maintained in the native state and is not crystallized out. After that, the aqueous sample solution applied on the grid mesh and frozen using liquid ethane or a mixture of liquid ethane and propane. So after freezing, it is observed under electron microscope and data is collected. So data can be collected from many different angles. All the different angles are kind of collected and summed together to get a 3D image of the object. So suppose you are looking at this protein from many different angles, like the top, the side, the bottom at an angle. So for each, you will get a different 2D image. When all the 2D images are summed together to get a net 3D picture of the protein, then you can reconstruct the picture of the protein as it is in nature. So while development of this technique began in the 1970s, recent advances in detector technology and software algorithms have allowed for the biomolecular structures at near atomic resolution. That means that you can get the structure of the protein not just at its surface, but up to the level of each individual atom. There are many different terms associated with microscopy. First is the resolving power. So the power of an objective lens, which is able to separate two distinct adjacent points, is called the resolving power. So suppose you have two atoms very close or cells very close to each other. If you can see the two separately, then it is said to be well resolved. If the two are merging, then it is just resolved. And if they merge completely so that you can see a single point, then it is not at all resolved. There is a numerical formula to calculate the resolving power, and that is lambda by 2Na, where lambda is the wavelength of the light that is falling on the microscope, and Na is the numerical aperture of the lens. So what is the numerical aperture? This term, the numerical aperture, characterizes the range of angles over which the system can accept or emit light. It is the ratio of the diameter of the lens to its focal point. So if this is the lens, the length of the lens is called its diameter, and the focal point is that point. So if you have a parallel beam of light passing through the lens, the beam gets focused at a single point called the focal point. And the length from the middle of the lens to the focal point is the focal length called small f. So to calculate numerical aperture, it is the ratio of d by small f. Numerical aperture can be decreased by decreasing the amount of light that passes through a lens. So if you look at this image, this is a larger lens through which a lot of light is passing. And this is a smaller lens through which small amount of light is passing. So when there is a lot of light passing through the lens, you can see that its focal length is short. It is getting focused in a short distance. While when small amount of light is passing through the lens, the focal length is quite big. If the focal length is small, since it is in the denominator, the numerical aperture becomes big. That is why the larger lens has high numerical aperture and the smaller lens has low numerical aperture. Also, if you look at it in terms of the diameter, the larger lens has a larger diameter and so a higher numerical aperture. So you can increase the numerical aperture either by increasing the diameter of the lens or by decreasing the focal point. Another formula of the numerical aperture, Na, is small n sine theta, where n is the index of refraction of the medium in which the lens is working, and theta is the half angle of the maximum cone of light that can enter or exit the lens. So if you imagine two parallel beams of light coming at the very edges of the lens, that is the maximum amount of light entering the lens. And so this cone that is formed, if you imagine this, and over here, if you imagine a cone forming, this is the maximum cone of light that can exit the lens. If you draw a normal from this focal point to the middle of the lens, then half of the angle of this cone is theta. And if you take n sine theta, where n is the refractive index of the medium, in air the refractive index is generally 1. So if you take n sine theta, that also gives you the value of the numerical aperture. The third term associated with microscopy is called magnification. Magnification is the process of enlarging something only in appearance and not in physical size. So if you remember the principle of the compound microscope that we studied, so this is the actual object. It is initially slightly magnified using the objective lens to get a real image, and then it is hugely magnified by the eyepiece lens to get a huge virtual image. So the initial object has been magnified in appearance, but not in physical size. So the size of the object is same. This is just an imaginary image that has formed. And this process is called magnification because you're getting a much larger image. Now, microscopy is of two types, bright field and dark field microscopy. The ordinary microscope is called as a bright field microscope. It forms dark image against a bright background. So this is an image formed by a bright field microscope. The background is bright and dark spots are formed to get the wherever there are cells or atoms or whatever you're observing. A bright field microscope can be adapted as a dark field microscope by adding a special disc called a stop to the condenser. So if you just remember the principle of microscope that we learned so far, you have the specimen, which initially the light passes through the specimen to the objective lens. And then from the objective lens, it reaches the eye. So this is the principle of the bright field microscope or the ordinary microscope that we have studied so far. This setup can be modified by adding an opaque disc called a stop before the condenser lens. So what this will do, only light reflected by the specimen is captured by the objective lens. So what this opaque disc does is that it blocks the light from everywhere except where there is the specimen. So the image from the dark field microscope will have a dark background, and wherever the cells are there, there will be a spot of light. So as I said, this opaque disc or the stop is blocking all the light from entering the objective lens, except the peripheral light that is reflected off the sides of the specimen. In other words, wherever the specimen is not there, the light is blocked over there by this disc. But wherever you have the cell, the light bounces off the sides of the cell and gives a bright image. So that is the dark field microscope. There are several drawbacks of light microscope, which is why the electron microscope was required. So electron microscope was invented because of the drawbacks of the light microscope. Light passing through slits get diffracted, and the convex lens collects the diffracted light. After collection, it produces the slit on the screen. So this is showing a disadvantage of the light microscope. What happens is when the light passes through the specimen, now the specimen is kind of like a diffraction grating, because between two cells there is a certain empty space, or between two atoms there is a certain empty space. So that empty space can act as a diffraction grating, and so whenever the light is passing through the specimen, it gets diffracted or scattered before it reaches the objective lens. Now these diffracted rays, after passing through the objective lens, they can either have constructive interference, in which case you will see a coherent image like this. Suppose the specimen is an alpha helical molecule, you will see a coherent image. But suppose the diffracted rays have a destructive interference, then the image is completely messed up and blurry. So this is a disadvantage of the light microscope, which is the possibility of diffraction. With the width of the slit decreased, the diffraction increases. So suppose the spacing between two cells is decreasing, the diffraction increases even more, as a result of which the image will become even more blurry. The way to solve this was proposed to be electron microscope. So before that, we learn about something called the de Broglie equation. So this equation is used to describe the wave properties of matter, specifically the wave nature of the electron. So the equation is lambda equal to h by mv, where lambda is the wavelength, h is the Planck's constant, m is the mass of a particle moving with velocity v. So suppose an electron of mass m is moving with velocity v, then the electron will have a certain wave nature associated with it, which has the wavelength lambda. So the electron has both particle as well as wave nature. Now the mass of an electron is around 9.1 into 10 to the power minus 31 kg. Comparatively, the mass of a photon is much lesser. So like around the order of 10 to the power minus 38 kg. So if the mass of the electron is large, its wavelength will be small. And we know that if it is a small wavelength, it can easily detect smaller particles. That is why the scope of the electron microscope is even larger than the light microscope. So just one second. Suppose suppose this is your photon wave, and the virus that you want to study is very small, just this size. The wave will completely pass through the particle and you won't be able to study it. But the electron wave, since the mass of an electron is much larger, its wavelength is much smaller. So an electron wave will kind of interact with the particle because its wavelength is much smaller. And so you can actually observe much smaller particles using electrons compared to photons. So photons are used in the light microscope. And so the light microscope has a maximum range of up to 100 nanometer. If you want to observe something smaller than 100 nanometer, you need an electron microscope. There are different types of electron microscope. The first one is the transmission electron microscope, or TEM. So an electron microscope uses a beam of accelerated electrons as a source of illumination. Electron microscopes use shaped magnetic fields to form electron optical lens systems that are analogous to the glass lens of an optical light microscope. So what this means is that where the light microscope was using a beam of light, that is a beam of photons, electron microscope uses a beam of electrons. And light microscope uses lens in order to bend the light rays, whereas the electron microscope uses magnetic fields. So you know that a moving electron has a magnetic field. So if you make it pass through a magnetic field, it will bend. So similarly, as light passing through a lens will bend, an electron passing through a magnetic field will bend in order to give you the image that you need. So this is the setup of a transmission electron microscope, or TEM. So the electron beam is produced by an electron gun, commonly fitted with a tungsten filament cathode as the electron source. It is accelerated by the anode, typically at 100 kiloelectron volt with respect to the cathode, and focused by electrostatic and electromagnetic lenses and transmitted through the specimen. So basically, an electron gun consists of a tungsten filament. Now, if you heat that filament, electrons will be emitted by a process called thermionic emission. And then you have the anode, which is positively charged. So when electrons are emitted by the electron gun, the positively charged anode will accelerate the electrons towards it. So the electrons are now accelerated till it passes through different lens, like the condenser lens, which is condensing all the electrons into a single focal point. So the condenser lens basically has different electromagnetic fields which can interact with the electrons and force it to condense at one particular focal point on the sample. Once all the electron rays pass through the specimen, it carries information about the structure of the specimen that is magnified by the objective lens system. So you have the electron rays which are passing through the sample. And after passing through the sample, it will carry all kinds of information like the spacing between the different cells, the shape of the cells, similar to how the light microscope, the information was carried by the rays of light. In electron microscope, these electrons, after passing through the specimen, will carry that information. And similarly, how in light microscope and objective different lenses were used to magnify the image. Here also the objective lens, the aperture lens, these are used in order to magnify the image of the object after the electron rays pass through it. Finally, it reaches a fluorescent viewing screen, which gives an image wherever the electron strikes it. So basically the use of the fluorescent screen is that wherever the electron is striking the screen, a spot is formed. So like that, the image is formed of the object. The resolution of the TEM is limited by spherical aberration. So we had learned about spherical aberration, where if you go back, spherical aberration was where there was a problem in focusing the light rays because there was different degrees of refraction. So the rays passing through the corners were refracted more, and the rays passing through the middle were refracted less. So due to this, spherical aberration can also occur in electron rays. So due to this spherical aberration, there is a limit of resolution, because when this aberration happens, you get a blurry image. This is often solved by using high resolution transmission electron microscopy, or HRTEM, where you can get a resolution to below 0.5 angstrom. And the magnification is above 550 million times. So it is a huge magnification, much greater than that obtained by the light microscope. The disadvantage of the transmission electron microscope is the need for extremely thin section of the specimen of around 100 nanometers. So basically, if your specimen is thick, the electron will not pass through it, because you have to remember that the electron is not like the photon. In light, even if the specimen is a little bit thick, the light will pass through it because the size of the photon is very small. But the size of the electron is much larger than that of the photon. So only if the sample is very thin will your electron rays pass through it to give the image. So that is the disadvantage of transmission electron microscopy, because it is difficult to create such a thin sample, which has a thickness of around 100 nanometers. The second kind of electron microscope is called a scanning electron microscope. So in this, what happens is that electrons are produced at the top of the column and accelerated down and pass through a combination of lenses and apertures to produce a focused beam of electrons which hits the surface of the sample. So the beginning part is very similar to that of TEM, but in scanning electron microscope, what happens is that once the electrons are generated and they pass through the lens, a beam of electrons is focused on the sample. In transmission electron microscope, the beam was passing through the sample to give the image. But in SEM, what happens is that the concentrated beam of electrons hits the sample and gets scattered in different directions. The position of the electron beam on the sample is controlled by scan coils situated above the objective lens. These coils allow the beam to be scanned over the surface of the sample. This beam scanning enables information about a defined area on the sample to be collected. So suppose the beam is first focused at the middle of the sample. From the reflected beam reaching the detector, you will get an idea about this portion. Then using the scanning coil, the beam is moved so that it focused on the sides. And then you will get information about the sides of the sample. The characteristic of this type of microscopy is that you are getting all kinds of information about the surface topography of the sample, but nothing about the interior parts, because the electron beam is not passing through the sample to give you information about the interior structure of the sample. It is only giving you an idea about the surface topography. So as the electrons interact with the sample, they produce secondary electrons, backscattered electrons, and characteristic X-rays. So if you look at, suppose this is the sample and the electron beam reaches the sample, many different kinds of rays are emitted from it. They can be different kinds of characteristic or continuum X-rays, or they can be secondary electrons. Like suppose the electron beam hits the sample and an electron of the sample is ejected. So that will be a secondary electron. All these rays are collected by detectors to form the image, which is then displayed on the computer screen. Normally, full-sized SEMs provide resolution between 1 to 20 nanometer, whereas these desktop systems, where it is connected to a computer, can provide a resolution of 20 nanometer or more. So scanning electron microscopy is used when you want to learn about the surface topography of the sample, and transmission electron microscopy is used when you want to learn about the inner structure of the sample. So how did the initial discovery of cryo-electron microscopy happen? There were many challenges in studying the structure of biological material. It was noted that electron microscope could not be used to study biological material without the destruction of organic cells by the intense electronic bombardment. Preventing such destruction would require a new sample preparation technique. So in electron microscope, when a beam of electrons is concentrated on the sample, what happens is that organic samples often get destroyed. So if you look at these two images, this is a low level electron beam where the sample is intact, but you cannot see the structure very nicely. If you increase the intensity of the electron beam in order to see the structure with more resolution, the structure gets completely destroyed. As you can see here, this is on the right side, this image is when a high energy electron beam is used. All these cells are completely destroyed, and so it appears as a bloody gray region. So you need a high energy electron beam in order for good resolution. But if the energy of the electron beam is too high, then the sample itself gets destroyed. So something was needed which is more advanced than normal electron microscopy in order to study biological samples. Another problem was how to preserve water in the biological sample in the vacuum maintained inside the electron microscope chamber. So the electron microscope can only operate in a vacuum chamber, or because otherwise the electrons that are generated will get quenched by the molecules of air. So in this vacuum, what happens is, suppose you have a protein which is stabilized by interactions with the surrounding water. In vacuum, what will happen is that this water will get evaporated and the structure of the protein will completely break down because the structure was maintained by interactions with the water. So when the water is taken away, the protein structure is completely destroyed. So a method needs to be taken such that the water is maintained even in the vacuum of the electron microscope chamber. And finally, the third challenge was that intact biological material has very low image contrast, as most high energy electrons pass straight through the specimen. So in biological materials, what happens is that most of the electrons pass through the specimen. So only the electrons which are hitting the specimen will give an image. Since only around 5% of the electrons are hitting the cell or biological material, a very faint image is formed. What is needed is a much clearer image. So the strategy for solving this problem was cooling the biological material or the use of an approach similar to negative staining. We will learn about both these in subsequent slides. And another thing that had to be maintained is the probability of multiple electron scattering events must be negligible at the electron energy used. That is, the sample must be thin. If the sample is not thin, different layers of the sample can scatter the electrons differently, and that will cause even more confusion. This is how, because of the drawbacks of the electron microscopy, that cryo-electron microscopy was developed. Just give me 1 minute. So in cryo-electron microscopy, the first step was sample preparation. To perform single particle electron microscopy, thousands of identical particles are imaged and computationally averaged together. The ideal single particle specimen is thus as homogeneous as possible. Heterogeneity can result from both conformational variation and flexibility, or by compositional changes. So the first step is to completely purify the protein. Like here, if you see on the left, it shows a mixture of proteins, and on the right, the single band is indicating that it is a pure protein. So only when the protein is very pure can cryo-electron microscopy be done. There can be two kinds of impurities. Firstly, compositional variation, meaning that there is something, some impurity that has crystallized along with the protein. So this can be reduced by using biochemically appropriate protein purification methods. We had learned, there are different kinds of chromatography, like size exclusion chromatography, which can purify a protein. So removing the impurities will reduce the compositional variation. But even this does not ensure that the sample will be homogeneous in the electron microscope. The greater problem comes from conformational variations. Like suppose you have a protein which has a long side chain of amino acids. The side chain can occupy any conformation. And so because of this difference in conformations, the electron microscopy will give a blurry image. So it is necessary that this conformational variation is also reduced. For this, an optimum buffer condition needs to be found where the conformational variation is minimum. Another way of reducing the conformational variation is known as chemical cross-linking, where what happens is that suppose you have two free side chains. If they are left free, then they can adopt any conformation like alpha helix or beta sheet, and that will give a blurry image in the electron microscopy. But if you covalently cross-link the two side chains such that they do not change conformations and remain parallel, then the electron microscopy will give a clear image. The problem with this may be that we are introducing a new chemical element, and this can change the native structure of the protein, and it can adopt a non-native or non-functional form. So that is the drawback of this chemical cross-linking. The other approach to reduce the conformational flexibility is ligand-induced stabilization. Suppose you have this molecule, which has many antiparallel beta sheets. Suppose this molecule is not very conformationally stable, and it can go from a beta sheet to a non-beta sheet conformation. Now, when this ligand is complexed with this molecule, then it remains in a very stable beta sheet conformation. So by complexing with the ligand, the conformational flexibility is reduced and it is maintained in a single conformation. Because of that, it will give a very clear image in the electron microscope. The second step of the cryo-electron microscopy, once the sample has been purified and homogenized, is called grid preparation. So to image with electrons, a microscope is maintained under a high vacuum in which the hydrated biological specimens would dehydrate rapidly. Thus, to image a biological specimen, it must be fixed, preferably in a native state. So like we saw before, that in the vacuum of the electron chamber, the water will be evaporated, leading to a destruction in the native structure of the protein. So somehow the biological specimen has to be fixed in its native state. Another consideration is the sample thickness. In some cases, the sample may be too thick for the electrons to be transmitted, which is a prerequisite for transmission electron microscopy. So the specimen must be thinner. So right now we are learning about transmission electron microscopy, where you saw that the electron needs to pass through the sample. And so the sample thickness must be very less, because in a thick sample, the electrons will get blocked and it will not pass through the sample, and so no image will be formed. So the sample thickness must also be maintained at low values. Electron microscopy grids are generally 3.05 millimeter across and made from a mesh of metal. Generally, copper grids are used, but gold supports are becoming more common, especially when the cells are to be grown directly on the grid, as gold is non-toxic to cells. So often cells can suffer from copper poisoning from the copper grids, which destroys the cell. And so in those cases, gold is used because gold, as you know, is a noble metal, which makes it unreactive. And so in those cases, this grid is made from gold. The metal mesh supports the film on top. Over the metal support, the film is deposited. So if you look at this metal support, if you look at a single square in this metal support, in this square, there is a carbon film, and on the film, there are holes like this, which can hold the protein samples. So it is basically 3 levels of organization. Firstly, on the grid, there are squares in which there is a carbon film with regular holes. And in each of the holes, if you magnify them, the biological specimen is suspended. So finer mesh sizes provide more support for the film. So if the mesh is very fine, the film has a lot of support. But the problem becomes that the bars in the mesh can block the electron beam. So your grid cannot be too crowded, because then the bars of the grid will block the electron beam. But if the grid is very less crowded, then it will not properly support the film. So compromise needs to be made, and it has been seen that 200 mesh grids are the best for the data collection. The next part of cryo-electron microscopy can be of 2 types. One type is the negative staining. So negative stain is a common method for examining a specimen, especially macromolecular complexes. And the advantage of this method is that it occurs at room temperature and its speed is very high. So typically, the specimens are adsorbed onto a thin continuous carbon support film. It is then stained with a solution of heavy metal salt, commonly 1 to 2% uranyl acetate or formate, which generates a cast around the object. The cast scatters electron more strongly than the encapsulated material and thus generates a relatively high signal to noise ratio. It is more resistant to electron damage and prevents collapse of the biological material during drying in vacuum within the electron microscope. So basically, if you look at the working of negative stain, is that you are studying this cell, suppose, and this cell is negatively charged because of the cell is negatively charged because you are bombarding it with electrons, and you have a stain containing a positively charged chromophore. So the stain will occur in all regions where the cell is not there. Wherever, since the surface of the cell is negatively charged, the stain will only form at the surface of the cell, and the inner parts of the cell will be unaffected. So the stain forms a kind of coat around the cell, and this coating is scattering the electrons very strongly. So if the electrons were directly scattered from the surface of the cell, it will give a low intensity image. But once the positively charged stain is combining with the negative charge on the cell surface, it is scattering the electrons very strongly. So a high signal to noise ratio is generated. Secondly, which was a problem with electron microscopes, is that high energy electrons would destroy organic materials. So this stain, which is forming a coat around the cell, is also protecting the cell from damage by high energy electrons. And secondly, and thirdly, what the stain is doing is that it is preventing the evaporation of water molecules, which would lead to the destruction of any protein structure within the cell. So the coating of the stain around the cell helps in three ways. It increases the signal noise ratio, it reduces the radiation damage to the cell, and it prevents the water molecules from drying up and destroying the protein structure. The drawback of negative stain is that often while the staining is happening, the cell shape may change. Additionally, the structures are limited to modest resolution. So basically, you are observing the granularity of the stain. And so depending on if the stain is made up of very small granules, then you can observe the structure to high resolution. But there is a limit to which the stain, there is a limit to the size of the granules of the stain. That is why this technique can only provide modest resolutions greater than 20 angstrom. Another problem is that you can only have information about the surface of the cell. Since the staining is only at the cell surface, you will get information only about the cell surface and not about the interior of the cell. And often the stain can be incompatible with the buffer medium in which the cell is stable, or the staining can affect other impurities, which is not the cell that you want to examine. So these are the negative drawbacks of negative staining. Another drawback is if a continuous carbon support film is used, then it can orient the cell in a specific orientation. So how the image formation happens is that you have to have the 2D picture of the protein from many different angles. But if the protein gets fixed in a certain orientation, then you will get the 2D picture only from very few angles. And so it will be very difficult to reconstruct the 3D image of the protein. So that is another problem with negative staining. Due to this, a better technique was developed, which is called vitrification. Vitrification is mainly what is used in modern cryo-electron microscope. So sample preparation techniques such as staining involve the dehydration of biological specimen, which removes them from the native aqueous environment. So we want to preserve the aqueous environment of the biological specimen so that it is maintained in its native structure. Cryoimmobilization preserves the aqueous environment while also reducing the radiation damage. So what is done is, firstly, the sample is transferred to the metal grid such that a thin film is formed, and then it is rapidly frozen at a rate of 10 to the power 6 degrees Celsius per second, so that the water in and surrounding the specimen is fixed in a vitreous state. This means that whatever conformation the water has in the native state of the protein, it is frozen in that conformation only. So basically, suppose this is a cell and you are freezing it slowly, then the water will come out of the cell and form ice crystals on the surface of the cell, and the shape of the cell will completely change. So this is not a good method because the shape of the cell itself is changing. But in vitrification, what happens is that the shape of the cell is completely maintained and the water becomes ice and freezes in the same conformation as it is in the native cell. So if the freezing occurs too slowly, or if the specimen is warmed above minus 137 degrees Celsius, then crystalline ice is formed and the cell is completely deformed. So normally temperatures of around minus 196 degrees Celsius is used either by liquid nitrogen or liquid propane or ethane, so that the ice crystals do not form. Rather, the water is frozen exactly in the same conformation as is present in the native state. Ice contamination compromises the structural integrity of the specimen as crystals withdraw water molecules from hydration shells of the specimen or the specimen itself. Formation of crystalline ice also degrades image quality as they diffract electrons. So if ice crystals form, not only does the shape of the cell completely change, but the electrons which are striking the cell also get diffracted by the ice crystal, and so very poor quality image is obtained. So the method that is used called vitrification is where suddenly this mesh, this grid containing the specimen is very rapidly plunged into the liquid nitrogen or ethane and immediately removed so that the ice is vitrified, that is, it is frozen in the same conformation that is present in the native protein. Another method is called high pressure freezing. So here what was being done is that this is called plunge freezing, where the mesh with the sample is plunged into the liquid nitrogen and immediately taken out. In some cases, this is not possible. Like when samples are thinner than the edge of a large cell, they can be vitrified by plunge freezing. Thicker samples, meaning less than 1 micrometer, such as nuclear and perinuclear regions of eukaryotic cells or tissue sections, are likely to experience some crystalline ice formation during plunge freezing. For these specimens, high pressure freezing or HPF is an effective alternative. What this is basically saying is that if you have a very thin specimen, you can freeze it like this, that you suddenly plunge it into liquid nitrogen and take it out and it becomes vitrified. But if you have a thick specimen, that will not work. So what happens in the HPF method is that the pressure of the sample is raised to around 2000 bar while dropping the temperature using liquid nitrogen. So suppose this is a living cell and you are freezing at the normal pressure, that is the normal atmospheric pressure. So like this, hexagonal crystals of ice will form and it will completely distort the structure. So as you can see, this was a very nice cell membrane structure. The structure gets broken when the crystalline ice is formed. But if you do the freezing at high pressure, then the water crystals will freeze in the same orientation that they were in the cell, and the structure of the cell is also not disturbed. So this is the advantage, that the sample is preserved in the native state, and so we can get high resolution 3D information. The disadvantage is that in order to be visualized by transmission electron microscopy, the sample must be sectioned or thinned by focused ion beam milling after freezing. So basically, for thick samples, you can freeze it using high pressure freezing, but you can, in order to observe by the transmission electron microscope, the sample cannot be thick. It must be thin enough that the electron passes through it. So a focused ion beam is used to slice the sample into thin slices after this freezing, and this slicing can cause a lot of complications. So that is the disadvantage of this technique. A common alternative approach is to perform freeze substitution on the sample, which enables sectioning and imaging at room temperature. Freeze substitution involves gradually warming the specimen and replacing the water with acetone. The sample can then be stained, embedded in resin, and sectioned. So basically, suppose this high pressure freezing is not possible because high pressure freezing requires a thick sample. What you can do is freeze substitution. So in freeze substitution, the water is replaced by acetone, and acetone is not going to form hexagonal crystals like this. Acetone will freeze in the same conformation as in the native cell. And so the conformation is not destroyed, and you can observe even thin samples. Now we will look at the electron source of cryo-electron microscopy. So the electron gun of an electron microscope extracts and accelerates electrons and can be either a thermionic emission or a field-assisted thermionic emission, such as the Schottky emission gun, known as the field emission gun. So thermionic emission is basically using a tungsten filament or lanthanum hexabromide crystals, and these are heated so that the electrons in the filament or the crystals gain energy from the heat and escape to form the beam of electrons. So here the voltage needs to be between 18 and 200 kilovolts. In field emission gun, what happens is that there is a very fine tungsten filament coated with zirconium oxide, and it operates at much higher voltages of 200 to 300 kilovolts. Here, these are much brighter and coherent compared to conventional thermionic sources. So they are preferred for high resolution electron microscopic studies. Here, what happens is that it is not heating that is causing the emission, but there are two anodes which create a very strong positive electric field, which withdraws the tungsten electrons from the fine tip of this tungsten tip. So here, because the filament is very thin, electrons from the tip will escape when the high electric field of two anodes is applied. So when a very high resolution structure is required, these FEGs are used. But they are significantly more expensive both to purchase and maintain. So the choice of the gun should be according to the experiment. For example, if negative staining is done, then you already get a high resolution image. So you don't need the field emission source. But if you're doing vitrification, then field emission source is required. So once the electrons are generated, they have passed through the electromagnetic fields, through the sample, and finally they will reach a detector which will detect and form the image. So there are certain characteristics of these detectors. Firstly, the electron microscopic images of the biological specimens are normally very noisy because low electron doses are used to prevent specimen radiation damage. So a perfect detector will be one that will add no noise. But in practice, all detectors add some amount of noise. In order to express this, there's a term called detective quantum efficiency, or DQE, for each detector, which is the square of the output signal to noise ratio with the input signal to noise ratio. Charged coupled device, or CCD cameras, utilize a phosphor scintillator which induces the emission of photons when electrons strike it. So basically, electrons will strike the detector, and wherever it is striking, photons will be generated. The CCD camera then transforms these photons into electric signals. A CCD chip has an array of photosensitive elements in which the electric charge accumulates. So what happens is that the electron strikes the detector and photons are created. These photons are transmitted into electron signals, and that electrical signal will pass through the CCD to the final detector, where the charge is read out, amplified, and digitized to form an image. So the electrons, after passing through the sample, strikes the detector. Photons are created. Photons are converted into an electrical signal. The electrical signal passes through the CCD and is read by the final detector to form an image. The scintillator layer results in electron and thus photon scattering causing a loss of sensitivity. So often when it reaches the detector, the electrons can become scattered, or even the photons after generation can become scattered. So if this happens, then the sensitivity is reduced. Despite this problem, the data collected on a CCD camera under appropriate imaging conditions can be processed to sub-nanometer resolution. So it gives very high resolution images. So once the detector detects the image, there is a process of data collection. Once the protein density and ice thickness or quality have been optimized, an initial data collection should be performed on a mid-range electron microscope. The goal is to obtain 2D reference-free class averages, which have high resolution features at the level of secondary structure. So after the initial data collection, what happens is you get many different images of the structure, say from the top, from the bottom, from the sides, from many different angles. You get a 2D picture of the structure. All these 2D pictures are put together, and that is called 2D classification. So 2D classification is when you take, so data collection is basically taking snapshots of the structure from different angles. And when you put all these snapshots together into kind of a movie, you have all the 2D pictures put together. That is the 2D classification. Once this is generated, a large data set with few hundred micrographs and several tens of thousands of particles is collected. So once you have an initial 2D data set, you can keep refining the data set till you have many different pictures of the structure from different angles. So from that, a 3D map can be created. So if you put together the pictures of the 2D pictures of the structure from different angles, you can get an idea about the 3D structure of the protein. Different points need to be considered. First, are the 2D pictures showing distinct views of the particle from different directions with features of secondary structural elements? Like suppose this particular one is kind of showing a helix from the top. Suppose you have another which is showing the helix from the side. So you can put those two together and figure out that it is indeed an alpha helical structure. Second, the orientation distribution needs to be sufficient to allow the calculation of the 3D structure. And if the orientation distribution is not sufficient, you need to optimize it by adding buffers, changing conditions, till you get sufficient number of pictures from different angles in order to reconstruct the 3D image. So now biological specimens are not static. They can move during or after the data collection. So each data set collected should be checked to verify that the specimen preparation and illumination conditions are optimized to minimize the particle motion. Currently, the simplest way to do this is using a per micrograph motion correction program called MotionCore. So each micrograph is collected as a movie subdivided into individual frames. The program, what it will do, it will detect the movement of the specimen looking at the different pictures, and then it will correct that movement. So if you look at A and B, A is shown where the specimen is not moving at all. So you have a distinct image. In B, the specimen is moving at the rate of 10 angstrom per second. So the image becomes slightly blurry. So this needs to be taken care of. That is basically, if there is a blurring of the image due to specimen moving, then many different pictures need to be taken with time. And then when it is put through the program called MotionCore, the program will correct for this movement so that you can get a clear image like this. This picture, what it is showing is that movement for 1 second on all gold versus amorphous carbon on gold support. So if you have, you learned about the grid a few slides ago. So if the grid is made up of gold, the movement is very small. So displacement is on the x-axis. So the displacement, as you see, is less than 1.5 angstrom. So that will give a clear image. But if carbon on gold or quantifoil grid is used, then the displacement varies from 5 to 35 angstrom, which is a large displacement. And so a blurry image will be formed. So often this, as we studied earlier, that this gold grid will be used where this carbon grid shows too much movement. So now that the data has been collected, it needs to be processed. The single particles are extracted from the micrograph and they are sorted and filtered using 2D classification methods. Just excuse me 1 second. Yes, so you will get many different images of the structure like this, and then they are sorted and filtered using 2D classification methods. So you have many different pictures like this, so you will choose only those pictures which are clear and represent different represent the structure at different angles. So that will form the 2D data set. Data from a large number of 2D projection images featuring identical copies of the protein complex in different orientations are combined to generate a 3D reconstruction of the structure. So suppose there are many molecules of the protein. They are oriented in different ways as shown here. And so you are getting the image of the particle in many different orientations. That is forming your micrograph. In the micrograph, you will particularly pick those images which are clear and representative of the protein in different orientations, and that will form the 2D average image. And the different 2D images are put together to get a 3D reconstruction of the overall 3D structure of the protein. For isolated macromolecular complexes, which are randomly oriented in solution, they can be trapped in different reaction states by vitrification. So the position and orientation of each particle must be determined for 3D reconstruction. And the more particles used, the higher resolution you have. So the more particles you pick, the more 2D averages you will have. And the more 2D images you have, you will get a more resolved structure of the final 3D image. So the orientation of particles is described in several ways, which are mainly called as Euler angles. So Euler angles are defined in two ways. According to the first definition, the orientation can be determined by using longitude and latitude and rotation. So if we assume the initial particle to be at the origin, then the image of the particle, this is the image from the top, this is from this side, this is from the x-axis. So different images can be obtained. And if we consider that particular latitude and longitude, we can describe that from which particular angle the image is being taken. The other definition takes into account the z and x-axis. So the initial position is determined by the z-axis, and then the particle is rotated, and the orientation is new orientation is defined from the new x-axis. So if there is a rotation around the z-axis, the x-axis will move from x0 to x1. And using the difference from x0 to x1, the new orientation is described. Similarly, the rotation can occur along the x-axis, and the movement of the z-axis from z0 to z2 will be used to define the orientation of the particle. Finally, this is how the 3D reconstruction is done. So the goal of 3D reconstruction in cryo-electron microscopy is to take a 2D projection and turn it into a 3D volume. This allows for the visualization of small structures within the sample. So you have the molecule in different orientations, and you get 2D projections from that particular orientation. It is essential to reconstruct the 2D projection because the information gathered from the projection itself is limited. So what is done is that each point in the 2D plane corresponds to a slice in the 3D volume. It is possible to obtain a 3D volume, get the 2D projection, then take a Fourier transformation of the projection. So if you take a Fourier transformation of the 2D projection, you will get a slice of the 3D volume. What this means is that you have the 2D projection. If you carry out a Fourier transformation on the 2D projection, you will get like these are two slices passing vertically and horizontally through the 3D structure. So Fourier transformation of the 2D image will give you the image of the slice of this protein vertically and horizontally. Then if you take the inverse Fourier transformation on the slice, you will get the net 3D structure. So you don't need to look into the mathematics of all this. These are all done by programs nowadays, but this is the principle of it. That from the different molecular orientations, you get the 2D projection images. After that, Fourier transformation is carried out on the 2D images to get an image of the slice of the protein. And finally, an inverse Fourier transformation is carried out to get the final 3D structure of the protein. Next, there is something called cryo-electron tomography or CET. 3D images of biological sample is obtained by a process called cryo-electron tomography, where a 3D reconstruction of sample is created from tilted 2D images. So if this is the structure protein that is there, the electron beam passes through different angles through the protein, and you get the image of the protein at different tilt angles. These raw images are recorded and stitched together to form the required 3D structure using computer software. So in cryo-electron tomography, basically the protein, a single protein molecule is used, but the electron beam is passed through it at different angles to get the image at different tilt angles, which are again reconstructed to get the final 3D structure. Then a process called image enhancement is carried out. Basically, image noise is the random variation of brightness or color information in images produced by the sensor. Cryoelectronic images are normally very noisy and have low contrast. So like suppose this green area, it appears as a single blurred area. Image enhancement will show the different parts within this area, that it is divided into different concentric circles. So this image enhancement is done to smooth the noise as well as to enhance the contrast. Electron microscopy, the resolution has greatly improved over the years. So if you look at this image, the resolution of the glutamate dehydrogenase used to be so low before 2013. But now the resolution is much better. If you look at the right side of the image, this is the resolution that exists now. So for a protein of this size, which is 334 kilodaltons, this 1.8 angstrom resolution to the right can be achieved only after 2012-2013. Then if you look at the structure of the HIV envelope, the resolution in 2003 was greater than 4 nanometers. And over the years, it has improved till in 2017, the resolution was greatly improved to 0.36 nanometer. Again, another progress of the cryo-electron microscopy was that unlike X-ray crystallography, in which crystals lock proteins in a single static pose, researchers can use cryo-electron microscopy to calculate the structure of a protein that has been flash frozen in several conformations and so deduce the mechanism by which it works. So what this means is that cryo-electron microscopy can give an idea about the dynamism of the protein. So this is a protein called V80pase, and 100,000 cryo-electron images of this protein was taken at different orientations to create a molecular movie of the protein. So all these 100,000 images, when put together and played one after the other, it shows the dynamics of the protein and how it is functioning as an enzyme. So once the protein structure has been determined, it is deposited in the protein data bank. This is the database for three-dimensional structural data of large biological molecules. These are generally obtained by X-ray crystallography, NMR spectroscopy, but recently structures obtained from cryo-electron microscopy are also increasing, and they are submitted by structural biologists all over the world, and it is freely accessible on the internet. Any experimental information regarding the biological molecules have to be submitted and validated before scientific publication. Currently, this is considered as the only repository for 3D biological macromolecular structure solved by different experimental techniques like X-ray crystallography, NMR, or cryo-electron microscopy. So there are different functional components in the protein data bank. First is the data extraction. So the protein data bank provides many tools to carry out data extraction. Like this function called PDB extract will extract and harvest data in the PDB or CIF format from structure determination programs. Then there is a tool called SF tool, which will convert structure factor files in different required formats. Then the tool called Ligand Expo, it will search the chemical component dictionary for the IDs of release ligands. So suppose you have discovered the structure of a new enzyme and you want to find out that what ligands can couple with the enzyme. So from the Ligand Expo, you can find out different ligands and you can simulate. So this is called a docking simulation. You can simulate whether the enzyme will complex with that particular ligand. And finally, Point Suit, this tool, it generates symmetry records for macromolecular assemblies with point and helical symmetries. So all the symmetry data is extracted by the Point Suit tool. Then comes validation. So validation reports contain an assessment of the quality of the structure and highlight specific concerns by considering the coordinates of the model, the experimental data, and the fit between the two. Easily interpretable summary information that compares the quality of a model with that of other models in the archive will help users of PDB data to critically access archived entries and to select the most appropriate structural models for their needs. So in validation, what is done is that there are different scores that are given. And it is compared. So suppose outliers, the outliers must be small. Ramachandran outliers means that orientations that are not in the Ramachandran allowed regions. So the number of this must be small. Then sidechain outliers are disallowed orientations of side chains. So that also the number must be small. Like this, validation report is basically, it is compared to X-ray structures of similar resolution or of the same protein in different orientations. It is compared to other X-ray structures already present in the PDB, and it validates whether the structure that you want to deposit in PDB is of sufficient resolution or not. Once the validation is done, there are different 3D structure viewers, which provides a graphical summary of the biological and structural protein features of PDB entities and how they correspond to the sequences. So you can just enter the PDB ID and get and download the coordinate and experimental data files and view the 3D structure of the protein using any PDB viewer like Discovery Studio or PyMol. And also the sequence of the protein is given, like this is a sequence view of the protein. It is clearly showing that what sequence adopts what secondary structure. Like this yellow arrow is a beta strand. So this portion is a beta strand. This is a turn. This is an alpha helix. So this is called a sequence chain view, which clearly shows that according to sequence, what is the secondary structure. Then there is something called a genome view, which will correlate the PDB sequences with the genome sequences and show that which region of the gene is responsible for that particular region of the protein. So these are all functions provided by the protein data bank. PDB has grown rapidly over the years. So from the time it began in 1971 till 2021, if you see, there has been a huge growth in the number of structures available in the PDB. And the maximum growth was observed around 2000 to 2010. And over 8 crore people are using PDB every day. So it is clearly a very useful resource for structural biologists everywhere. And cryo-electron microscopy, if you see that over the years, its use has also increased. So initially, it was mostly X-ray. Then slowly around 1999, NMR came into use. And then around 2010, cryo-electron microscopy, around 2010, cryo-electron microscopy gradually started. But now it is clearly this yellow number, if you see, cryo-electron microscopy over the years, it is becoming more and more used as a technique to find out the protein structures. So we saw the protein database. Another database is known as the electron microscopic database, or EMDB. So cryo-electron microscopy enables the determination of 3D structures of macromolecular complexes and cells from 2 to 100 angstrom resolution. And all the cryo-electron microscopy structures are deposited in the electron microscopy database, or EMDB. The major goal of this database is to firstly establish data validation methods that can be used in the process of structure determination. Then define the key indicators of a well-determined structure that should accompany every deposition. And finally, implement appropriate validation procedures for maps and map-derived models into a validation pipeline. So EMDB, what it does is that it freely provides the different procedures used to get a good resolution structure from cryo-electron microscopy. And it provides example structures that people can refer to find out whether their structure is valid enough. And it helps people to validate their structures using different correlation maps. So as you see from this graph, that the data deposition in EMDB is gradually increasing, and it has overtaken the deposition in PDB. So often structures that are solely determined by cryo-electron microscopy are deposited in EMDB. And if you see this light blue line, it was initially absent. and it picked up around 2002, 2003, and it has grown to even overtake that of PDB. Even the resolution has increased over the years. So if you see, initially, most of the resolution was greater than 5 angstrom. But in 2019, 3 to 4 angstrom resolution is maximum, and even less than 3 angstrom resolution has been achieved for many structures. So with the increase in development of cryo-electron microscopy technologies, the resolution is also improving per year. Another database is the nucleic acid database, or NDB, and it is a portal for three-dimensional structural information about nucleic acids. It contains information about experimentally determined nucleic acids and complex assemblies. People generally use it to perform searches based on annotations relating to sequence, structure, and function, and to download, analyze, and learn about nucleic acids. So even in the nucleic acid database, cryo-electron microscopy is gradually becoming a very important technique. So if you look at this red bar that determines the cryo-electron microscopy determined structures, you can see it has become almost equal to that of the X-ray crystallographic determined structures. And in the subsequent years, it is predicted to overtake X-ray and NMR. So nucleic acid database gives information all about the nucleic acids. And the final kind of database that we'll study today is called the Biological Magnetic Resonance Data Bank, or BMRB. It is a repository of data from NMR spectroscopy on proteins, peptides, nucleic acids, and other biomolecules. BMRB collects, annotates, archives, and spreads worldwide the important spectral and quantitative data derived from NMR spectroscopic investigations of biologically relevant molecules. For example, suppose you have a molecule N-acetylglutamine, then BMRB will provide you the 1D, 2D, different kinds of 1D and 2D NMR data. So it basically displays all kinds of NMR data. So BMRB is often used to identify an unknown ligand or protein. So suppose you choose this molecule, N-acetyl L-glutamine, and you look at its 1D spectrum, and you have an unknown 1D spectrum which is very similar to it. So you can match it and say that your unknown ligand is N-acetyl glutamine. So the goal is to empower scientists in that analysis of the structure, dynamics, and chemistry of biological systems, and support further development in the field of biomolecular NMR spectroscopy. Even for a unknown protein, uh, uh, different 2D and 3D NMR spectra are freely available in BMRB, and they can easily be accessed and compared with the NMR spectra of our unknown protein to find out any similarity in structure between the known and unknown proteins. So we have learned about 4 data banks: the protein data bank, the electron microscopy data bank, the nucleic acid data bank, and the biological magnetic resonance data. So this brings us to the end of the topics for discussion today, and we'll just go through some sample questions. So the first question is that the resolving power of the unaided human eye is what? I'll give you some time to work it out, and then I'll discuss the answer. So the correct answer is A, which is 0.25 millimeter. So very nice way to see this is that you can see that this picture is made up of many different lines. So the space between each line is 0.25 millimeter, but your eye is able to distinguish this. While this you can see does not have any lines. So this is kind of a small experiment to see that this is the resolving power of the human eye. Basically, just to recap, the definition of resolving power was the ability to see two different particles which are near each other, the ability to see them separately. So as two peaks in the spectrum. If they are merging, then it is called, it is just beginning to not be resolved. And if it is a single peak, then it is completely unresolved. So as I said, this image, the distance between the two lines is 0.25 millimeter, but we can distinguish this. So this is the resolving power of the unaided human eye. The next question is that what is the final detector of cryo-electron microscopy? So the answer of this is C, or charged coupled device. So if you remember, uh, in cryo-electron microscope, after the electron beam creates a beam of electrons which is condensed onto the specimen, it passes through the specimen and the objective lens, and then it is detected. So this final detector, what it consists of, is basically a scintillator. So when electrons strike the scintillator, photons are generated, and photons give rise to an electric signal, which is then detected to form the image. Direct detectors can also be used where the electrons will strike a fluorescent plate, and wherever the electron is striking, an image, a dark spot is formed. So from that, electrons are directly generating the image. But the image from direct detectors is not very well resolved. So indirect detectors are more used now, and it is called a charge coupled device because the electron is kind of coupled to the photon, because the electron striking the scintillation forms photons, and then photons again give rise to an electric signal. So kind of the photons and electrons are coupled, and so it is called a charge coupled device, and the answer is C. The next question is that surface topography can be visualized by which of the following technique? So the correct answer is scanning electron microscope, or SEM. So if you remember, the concept of the scanning electron microscope is the electron beam is generated and condensed by different lens onto the sample. So it does not penetrate through the sample. It strikes the surface of the sample and bounces off to the detector. So if the sample has, suppose, peak, then a trough, it will detect the sample, the surface topography of the sample. So it will be able to, like, this is an image from the scanning electron microscope. You cannot see what is inside each of these particles, but you can clearly see the surface topography. Where there are peaks, where there are troughs, you can clearly see it. So scanning electron microscope can help you visualize the surface topography because it does not penetrate through the sample. It just bounces off, and the ray that bounces off from the sample gives you the picture of the surface of the sample. The fourth question is that what is the full form of PDB? So the full form of PDB is Protein Data Bank. And as you remember, it is the repository where all the protein structures are deposited, which have been determined by different methods, mainly X-ray crystallography and NMR. But recently, the use of cryo-electron microscopy is also increasing. So the structures that have been determined by cryo-electron microscopy are also deposited in the PDB, or Protein Data Bank. Next, the whole virus can be best viewed by which technique? So the correct answer is cryo-electron microscope. So if you look at the limits of the different observation techniques, the limit of the naked eye is 100 micrometer. The limit of light microscope is around 0.25 micrometer, whereas the electron microscope can observe up to 0.05 micrometer. That is why in the naked eye, in the maximum, you can see the different mycelia of the different fungi. Light microscope can observe single cellular organisms, yeasts, or bacteria, but it is not enough to observe viruses, which are less than 0.1 micrometer. For observing viruses, electron microscopy is the only option. And so the correct answer is cryo-electron microscope, or C. The next question is that Which of the following term is used for rapid freezing of the sample at a rate of 10 to the power 6 degrees Celsius per second, so that the water in and surrounding the specimen is fixed in a vitreous state? So the correct answer is D, vitrification. So basically, if it is normal slow freezing, what happens is that firstly, you know that living tissue mainly consists of water, and water is part of a solution with many other molecules in the living organisms. When the tissue is cooled slowly, the water molecules within it gather and form ice crystals. So you can see the hexagonal crystals of ice form in which the water is separated out from the other molecules. The ice then pushes the other molecules found in the living tissue into a harmful concentrated solution. So if all the water comes together to form ice, the remaining molecules becomes a very concentrated solution. Like if you have sodium, potassium ions in the cell, they become very concentrated, and that is very harmful for the cell. This is what happens in normal slow freezing. Now, if you do vitrification, which is rapid freezing, after adding cryoprotectants, what happens is that it prevents the water molecules from gathering like this. The molecules slowly slow down as it is cooled, and below minus 100 degrees Celsius, the molecules become locked in space and the solid is formed. So the solid ice is formed by locking the water molecules in the same position as they are in the native structure of the protein. That is why vitrification is used, because it simply locks the molecules in their positions, and so the cell is not destroyed. But if hexagonal crystal ice is formed like this, then due to the other ions and solids becoming very concentrated, the cell becomes destroyed. So this rapid freezing is called vitrification, and the freezing occurs at a rate of 10 to the power 6 degrees Celsius per second. The next question is that the internal structure of a bacteria can be best viewed by which of the following technique? So here the correct answer is C, transmission electron microscope, or TEM. So if you compare scanning electron microscopy SEM and transmission electron microscopy TEM, in SEM the electron beam is concentrated to fall on the surface of the sample, and the scattered electron beams is detected. But in transmission electron microscopy, the electron beam passes through the sample and the image is formed. So scanning electron microscopy only gives you an idea about the surface topography of the sample. It tells you about the surface, like where the peaks are, where what is the shape of the surface, but it cannot tell you about the interior of the sample because the ray simply bounces off the surface. It does not go through it. But in transmission electron microscope, the electron ray passes through the sample, so it can tell you all about the interior structure and imaging of the sample. So this is the image of SEM versus TEM. So since the question is that what is the internal structure of the bacteria, it can be viewed by TEM or transmission electron microscopy. And so the correct answer is C. The next question is, which is the first 3D electron microscopy structure released in the PDB? So the correct answer is D, bacteriorhodopsin. So this was the initial electron microscopy structure that was obtained. So this is a 2D representation, and many of the 2D snapshots were put together to get a 3D picture by 3D reconstruction, as we have learned. And it was found that the structure of bacteriorhodopsin consists of multiple alpha helices. Uh, and the 3D structure is formed by three such clusters, which are held together by various helical interactions. So bacteriorhodopsin is the first 3D electron microscopy structure released in the PDB. The ninth question is that how many years have we been celebrating PDB on 2021? So basically from the year that PDB was started till 2021, how many years has it been? So the answer is C, or 50 years. So basically, PDB was founded in 1971 by Brookhaven National Laboratory, New York. So from 1971 to 2021, it has been 50 years. And uh, through the years, the number of release structures per year has been increasing almost exponentially. So the correct answer of this is C, 50 years. The 10th question is that the power of an objective able to separate distinctly two adjacent points is known as what? So if you remember, the answer is B, or resolving power. So just to recap, resolving power is the ability of the instrument to distinguish between two separate spots which are close to each other but which are not the same spot. So in the first image, it shows clearly well resolved image with so if you look at the spectral peaks, it will show two clearly well defined peaks. Here the resolution is poor, the two spots are merging, and here it is completely unresolved because it appears as a single spot. So this power of the instrument to distinguish between these two adjacent objects is called the resolving power. So the correct answer is B. Next, how do you calculate the resolving power of a microscope? So the correct answer is A, that is D equal to lambda by 2Na, where D is the resolving power, lambda is the wavelength of the light used, and Na is the numerical aperture. So if you look at this resolving power of a microscope, so basically if this is your object and this inner circle is the image formed, then the resolving power is basically the ability of the microscope to distinguish between this image and an image very near it. So here you have uh, two examples of numerical aperture. In first case, the numerical aperture is 0.2, and with smaller numerical uh, so yeah, sorry, this has been exchanged. So basically, with smaller numerical aperture, the image becomes very blurry because the resolving power is high. High resolving power means that only when the distance between two objects is large, can you observe them separately. That is why in small numerical aperture, the image appears blurry. And when the numerical aperture is much larger, the resolving power is low. And low resolving power means you can easily distinguish between these objects which are very closely spaced. And so the clear image is observed. You can clearly see when you have taken a high numerical aperture, you can see, you can distinguish between these spots which are very close to each other, but which are not the same spot. But when the numerical aperture is low, all of them appear as a blurry image. And so the formula to calculate the resolving power is D equal to lambda by 2Na. The final question is that long wavelength, high diffraction, and less resolution are characteristic of what? So the correct answer is B, or red light. So as you know, the wavelength of red light is greater than blue light. Secondly, red light having a longer wavelength gives a broad diffraction pattern. whereas blue light having shorter wavelength gives a narrow diffraction pattern. Uh, and finally, the wavelength of red light is longer, so the resolution will be smaller. Because suppose you have a small atom, it can't be detected by the long wavelength of the red light, but it can be detected by the blue light. So the correct answer here is B, or red light. So that brings us to the end of, sorry, that brings us to the end of today's presentation. And I'll just give a few minutes for asking, 1 minute or so for asking questions. And if you have any questions later, you can always email them to me. Right. I think there are no questions for now. So I'll just stop the class here.